Learning objective 1.7. I can explain the relationship between trends and atomic properties of elements and electronic structure and periodicity. Okay, what's the key word there? Explain. This is not memorize and regurgitate. This is explain. Okay, the key word is explain. And Coulombic attraction or Coulombic force is our key to being able to explain. All right, at this point, I hope we know that the periodic table is organized in a way that helps us see recurring patterns and properties, as well as our electron configurations like we talked about last time. Okay. One thing I want you to note here that's going to be important to us as we look at trends in this first little blurb is the presence of completely or partially filled shells, okay, in electrons or atoms. Some of the anomalies that we see in our periodic trends are going to help us with that. Okay, the 4 trends that we look at with AP are ionization energy, atomic and ionic radii, electron affinity, and electronegativity. Okay, those are our 4 main things. I hope that we can very easily, now that we've gone through this POGL activity, here it is, fill some of these in. Okay, like nuclear charge, which is the charge of the nucleus, right? And the nucleus is going to contain protons and neutrons, so the nuclear charge is positive. What's a valence electron? Electrons in the? Yep, outermost energy level. These are electrons that are involved in bonding. Okay, what are our core electrons? What are they in between? 2 things. One would be the valence electrons, right? Okay, I'm going to do VE minus to abbreviate valence electrons from now on. Okay, they're between valence electrons and the nucleus. And they shield the valence electrons from a full attraction. Of the protons in the nucleus. Right, we just talked about that. All right, what's the relationship between number of core electrons and shielding effect? More core electrons means a higher shielding effect. Okay, the greater the shielding effect, what happens to the attraction between the nucleus and the valence electrons? It's going to be less. It's going to be weaker. Good. Now, again, the shielding effect has to do with the number of core electrons, which is really just our filled energy levels, right? We're talking more, okay, filled energy levels between the nucleus and our valence electrons. Again, greater the shielding effect, the weaker the attraction. We can see some trends both in groups and periods, not just for our periodic trends, but also for shielding and nuclear charge, right? For shielding, as we go in a group, okay, top to bottom of the group, what do you think happens as we go down? Okay. As we go down the group, what happens to the shielding effect? Does the shielding increase or decrease? It's going to increase because the number of core electrons will increase. We get more energy levels. We get more energy levels as we go down a group. What about a period trend? As we go from left to right across a period, what happens to shielding? It's going to be the same, right? That very first model, number 1, in the POGL activity showed us we have the electrons. So we're going to say that this is constant because our number of core electrons does not change across the period. Great. Great. Wonderful. Okay. Effective nuclear charge, you can abbreviate that ZEFF. Okay. Z effective, Z is for charge. This is the true force of attraction that we're going to have for those valence electrons. So we can say this is the force of attraction the nucleus actually has for the valence electrons. This is going to consider the core electrons. Core electrons will weaken the attraction between the nucleus and protons, or the protons of the nucleus and our valence electrons, because the core electrons will repel one another, okay, and they're also attracted to the nucleus. Just like the valence electrons are. This one I might circle, highlight, underline, box, whatever you want for yourself. Okay. Effective nuclear charge is the core charge. Okay. This is the number of protons minus number of core electrons. Again, effective nuclear charge is always going to be positive. Okay. Let's give her this. Let's look at group trends for effective nuclear charge. Again, we've already touched on this by discussing the Vogel. In a group trend for effective nuclear charge, in our same column, what happens? We already touched on this. In the group, the effective nuclear charge is going to be, you answered it for me already, Josh. What happens? Yeah, I know. Core charge, effective nuclear charge in the same group, in the same column, is going to be the same. There we go. Okay, this is going to be the same. This is going to be constant, and that's because, can I spell constant? My brain's a mess this morning too. Okay, that's because the core electrons and the total number of protons are going to increase, right? So as we go down a group, we add more core electrons, we add another energy level of electrons that are filled. So because that happens along with the increase of our number of protons in the nucleus, we're going to keep that constant. All right. Period trend for effective nuclear charge. We're going to cross our period left to right. What happens? It's going to increase. Okay. It's going to increase, right? Okay, so as we go across, we're going to increase. We're going to go left to right. I'm going to give a little arrow to show which direction we're going. Okay. This is because the nuclear charge increases while the core electrons will be constant. All right, now, here's the deal. Everything that we've talked about up to this point is actually all you really need to know for your periodic trends. You need to know what core charge, effective nuclear charge is, and understand the concept of shielding, and how those things come into play along with Coulombic attraction to be able to explain, right? Not regurgitate, explain the periodic trends. So every single trend is related to the attraction for those electrons for the nucleus. The attraction for the electrons for the nucleus are going to be affected by shielding, which really is related to distance from the nucleus, right? Okay, as we get further away from the nucleus with our valence electrons, there's going to be more core electrons and more shielding. So as we get electrons further from the nucleus and we have more core electrons, the force of attraction for the valence electrons is weaker. And that affects whatever the trend is that you're considering, right? As we stay in the same period and keep that constant, but we add more protons, the effective nuclear charge or the core charge is going to increase, and that increases attraction for the electrons to the nucleus. Being able to understand that in the context of Coulombic attraction, how it changes with distance from the nucleus, slash number of core electrons, slash shielding, and how it is affected when that stays constant, but the number of protons in the nucleus increases. It's going to be one or the other. There will be very few situations where you have to consider both a change in distance from the nucleus and protons, right? Okay, so keeping that in mind, these other trends that we're going to look at, size, ionization energy, electronegativity, electron affinity, which I like the least, I feel like it's least useful, okay, are all connected to this, okay? Now, in a perfect world, we would have had more time and we would have been able to play around with the collisions so we could see these patterns in ionization energy. I encourage you to do that on your own. I know it seemed at least that we enjoyed that when we looked at it for electron configurations. I'm going to show you in just a second what that looks like for the ionization energy, okay? Ionization energy is energy required to remove an electron from an atom in the gaseous state. Okay, you may want to note that, okay, atom or ion. So we're going to write a general equation for this. Okay, some atom in the gaseous state. We're going to turn that into a positively charged ion because we're going to lose that electron. IE for ionization energy, this would be IE1 because that's the first electron to be removed. Yeah? Okay. That first ionization energy is the energy required to remove the highest energy electron. Second ionization energy is the energy required to move an electron from a +1 ion. What's the relationship between first and second ionization energy? Greater than, less than, or equal to here. First ionization energy is going to be going to be less than second ionization energy. Let's think about this for a second before I show you this, right? Let's think about it for a second, right? And then we're going to fill in our little blanks here. If I take my atom, okay, it's got an equal number of protons and electrons, and I remove one of the electrons, tell me what's going on then. For the remaining electrons, are they going to feel a similar attractive force to the nucleus? Or stronger or weaker? It's going to be strong, right? We now have a difference here. We have less electrons, so there's going to be less repulsion occurring. Okay, so when we have that first electron being removed from a neutral atom, our second electron is being removed from a +1 ion. The positive ion now has one more proton than it does electrons, okay, which means the attraction is going to be stronger, so it takes more energy to remove. Okay, this is again due to Coulombic attraction. So I'm going to pull the collisions up really quick and just kind of show you this. I'm going to pull up magnesium so we can see these large jumps as well. Oh, let's see here if I can do this quickly. Hopefully collisions is actually still going to be functioning for me. I did have it pulled up and ready to go. But because I have the sandbox unlocked already, we'll see if this actually is going to cooperate. If it does, fantastic. If it doesn't, we'll just make it work. we'll talk about, oh, it's going to go. Perfect. My computer is working very hard to make this happen. I can hear it. I don't know if some of you can hear it too. I know, right? It's kind of ridiculous. Okay, yeah, great. All right. Where is it? There's sodium, there's magnesium. Oh, come back. All right, so there's my magnesium. Here's how this works, right? It's going to tell me how many protons and electrons I have. Notice I have an infinite number of electrons I can add, but then I have a certain number of units of energy here, right, where I can add or remove electrons. So I'm going to remove this electron. I'm going to pull it. Okay, so it tells me I used 8 units of energy to remove that first electron. Okay, cool, wonderful. All right, here's my second one. I'm going to pull it. See how it's taking more energy in order to do this? Okay, there it goes. Now I've got 23 units of energy that are used. I don't know if I can get this to move out of the way, but can we see? Go away. Can we see here that now I've got a nice full valence shell? Okay, now that I've removed 2 electrons, what's going to happen now when I try to remove a third electron? It's going to be way, way harder. Why? Give me multiple reasons. No, it doesn't want anything. These are not sentient atoms. They can't think, they can't want. So try really hard not to use that. So try again without using want. An atom is, there we go, when, you got it. Okay, so an atom is more stable when it's got a full shell of electrons, when the energy level is full, okay? The energy level is full of electrons. Okay, so that is one reason why it's going to be harder to remove. Give me a second reason, one we've already talked about. So, okay, electrons are closer to the nucleus now, which means they feel there's a stronger force of attraction for those electrons. Oh, great. Okay, can you give me one more reason why it's going to be even harder now? You got it. Okay, the ratio between protons and electrons is higher, okay, more protons compared to electrons, so we've got a stronger force of attraction. Okay, great. So let's just really see. I may not even have enough energy to do this. It may run out of energy, which it probably will. Okay, here we go. Okay, so it didn't even, I don't even have enough energy to do that, right? So that was significantly more, right? Significantly more. If I wanted in the game here, if I wanted more energy, I would have to add electrons into an atom that would release energy when that happens to become a more stable state with a full shell of electrons, right? So I do find this very helpful, this collisions. We just don't have enough time to do it together in class. Yeah? Okay, so I'm going to get out of this, and we're going to pull this back up. So then now we can wrap this up. So we just saw this, right? Here's our big jumps. This is for magnesium. We just saw this, right? This huge jump. From 2 to 3. Where's the other huge jump? 10 to 11. What happens at 10 to 11? Yeah, it's that other shell of electrons, right? It's that other shell of electrons. Okay, great. So we've seen this. We're going to fill this in here. Large jumps are due to the removal of core electrons, which are bound much more tightly. They're closer to the nucleus. We hit all the high points with that. Okay, wonderful. Ionization energy, first ionization energy. Okay, first ionization energy. As we go from left to right across the periodic table is going to do what? We're looking at our group trend, we're looking at our period trend. We're going from left to right across. first ionization energy is going to increase from left to right. Again, there's only one of two options. Here's the deal. If you're talking about a period trend, you are going to talk about which one, shielding or charge. Charge, right? Because the core electrons stay the same, okay? So anytime you're explaining a period trend, you're going to talk about nuclear charge, core charge, number of protons in the nucleus. They all mean the same thing, right? I don't care which one you go about using in your explanation. I will know what you mean. Your AP grader will know what you mean, okay? Doesn't matter. Do not ever give me valence electron number as an explanation for a trend unless you are comparing the size of an atom to its anion. That's the only reason that you would ever talk about number of electrons, and we will get to that when we get to that trend. Okay? So we looked at this on the Coulombic attraction total activity. Remember, there was one of the pieces asked you to compare the force of attraction when you have the same number of electrons at the same distance from the protons, and it didn't matter that there were multiple electrons. They were going to feel essentially the same force of attraction. You got it. So it's the number of protons, not the number of electrons. Okay. So here, from left to right, number of protons in the nucleus is going to increase, or increases, I guess would technically be the right thing here. Number of energy levels remains the same, which means the number of core electrons is not changing. Since the effective nuclear charge is increasing and the distance between the nucleus and the outermost electrons is decreasing, the outer electrons are bound more tightly to the nucleus and take more energy to remove. Therefore, first ionization energy increases as you move across the period. Great. Okay, that's a lot of words to say the stuff we already said. Yeah? Okay, we can definitely simplify that. Okay, same number of core electrons, greater number of protons as you move across, which means a greater force of attraction, more energy to remove it. Okay, as we go in a group trend, okay, the first ionization energy is going to decrease as we move down. Oh my gosh, let's just do an arrow because my spelling is not with it today. Okay, decrease. The electrons are being removed on average, are going to be farther from the nucleus. Increased distance between the nucleus and the outer electrons decreases the force of attraction for the nucleus and outer electrons. There are more core electrons between the nucleus and outer electrons, which means the shielding effect increases. Again, I'm going to go with an arrow. The nucleus has a weaker attraction for the outer electrons, therefore it takes less energy to remove as you move down the group. Okay. Do we understand this, how this pattern works? If we're talking about a period, we're going to talk about the increase in the number of protons and how that increases attractive force. If we go down a group, we're going to talk about more core electrons. Distance from the nucleus, as those two things increase, the force of attraction decreases, and that affects your trend. All right, let's get in electron affinity. Electron affinity is the energy change associated with the addition of an electron to an atom in the gaseous state. So here, we're going to have our general equation here. Okay, we're going to make an anion. I want you to circle, underline, highlight this little blurb here. If the addition of an electron is exothermic, a negative sign will be used, and this means that it is favorable. Energy will be released in this process. Okay, so now we're going to be able to use what we already know and have used for ionization energy to explain, again, that's the key word, explain the trend. So if we're adding in an electron, we're figuring out how much energy is going to be involved in this process. Really, whether you see a negative sign or a positive sign on electron affinity just really depends on the table that you're reading it from. We're going to try our best to keep them all exothermic and use a negative sign. Okay, so here, our period trend. Let's talk it through first. Okay, going across the period. Okay, we get more protons in the nucleus, which means an increase in the number of our core charge, effective nuclear charge. So when we do that, how is that going to affect the electron affinity? What do you think? It's going to be more or less favorable. Well, let's look through it. Okay, more negative, which is exothermic. Okay. As we go from left to right. More exothermic left to right. Okay, as we go across, atoms have to gain fewer electrons to become more stable, and more energy is released when that happens. Non-metals, okay, have more exothermic electron affinity than metals do. Right? It's all about the attraction. So as we go across from left to right, we increase the number of protons in the nucleus. Therefore, we increase attraction. Therefore, it's easier to add an electron, right? The greater attractive force makes it easier for that process to occur. Okay. A question like this, like we have here, why does nitrogen have a positive electron affinity and use electron configuration to explain? This is a situation where you would be given an anomaly in a trend and asked to use your knowledge of electron configuration, attractive force, Coulombic force to explain. Okay, so nitrogen, 1s2, 2s2, 2p3. For our 7 electrons. Let's check out this 2p3. 2p. How are we going to place these electrons? One in each orbital, right? 1, 2, 3. Okay. Same spin. If I'm going to add an electron, 1, 2, 3, that's 2p. 1, 2, 3, 4. What happens when I add that additional electron and now we've got 2 in that first orbital? Remember, they don't want anything. What do you know about electrons and other electrons? They repel. So what we've got going on here is more repulsive force. Compared to the half-filled 2p sublevel. Therefore, this is a less stable configuration. Okay, a less stable configuration. Yeah. Okay, we've got 2 electrons now in the same orbital instead of 1. Okay, think about, I have a lot of siblings. I also have 2 children, and they butt heads sometimes, right? If one kid is playing with one toy, the other kid wants to play with the same toy, and if they're in that same space right on top of each other, there is the ability for more conflict to happen. Yeah, can we go with this analogy for me? Okay, rather than one child playing with one toy over here, another child playing with a separate toy over there. Okay, if I add another kid into the mix, okay, so now we've got 2 toys only, or in this case, let's say 3 for our 3 orbitals for T. Okay, there's only the possibility if I have 3 kids playing with 3 separate toys and I add a 4th kid in, they're going to have to share with somebody, right? And that causes the ability for some conflict to happen. It's going to be a less stable situation because we've got sharing that has to take place, and that doesn't always work out very well. In the case of electrons, we're going to have repulsion that takes place because they're both negatively charged. So we have 2 electrons, even though they have opposite spins, one's clockwise, one's counterclockwise, they're still in that same space, so there's more repulsive force between them. That greater repulsive force is a less stable configuration than half-filled and each orbital having its own 1 electron rather than putting another one in to give that more repulsive force. Is that clear as to how the half-filled configuration is a more stable arrangement than having it partially filled with that additional electron in there? Now, what's the most stable situation going to be? Fully filled, right? Fully filled is going to give it the most stability because that's going to be lower in energy. The second best option is half-filled. Okay, anything else in there is going to give you a less stable, higher energy configuration. Yeah? Okay, good. Let's wrap this up with our group trend for electron affinity. Okay. As we go through a group for electron affinity, it's going to become more positive. Okay. Which means less energy is released. Because remember, these are negative, they're exothermic. Okay. Since the electrons are added at increasing distances from the nucleus. Okay, great. Now, radius and size we kind of looked at already in the atoms levels of collisions. If we take a look here, we can see what happens. But I want to just really quick, this will kind of be our last thing, we won't even fill anything out on this. We can see that the atomic radius decreases as we go across a period. Well, guess what? You're going to use the same explanation every time for a period trend, which is what? When you talk about a period trend, what are you going to use as your explanation? There's only 2 options. We're going to use protons, which you could also say what, besides number of protons? Charge in the nucleus, effective nuclear charge, core charge. All of those things are essentially telling you the same thing. As you add more protons in the nucleus, there's a stronger attraction for the outside electrons, which makes your atom smaller. Okay. Why does size increase as you go down group? We get more electron energy levels, right? Which means they're going to be further from the nucleus. We could also talk about shielding or core electrons, right? As we add more of them, they're not only further from the nucleus, but they also feel less attractive force. Okay? All right. Please start working on the practice problems for these, even though we haven't talked about electronegativity or size yet. You can at least get through some of these. Please let me know what questions you have. There are a lot of pages. There's 4 pages of practice for a periodic trend.